Section 7.1 is the logarithm defined as an integral. Part 1 of the fundamental theorem of calculus says that the derivative with respect to x of the integral from a to x of f of t dt is f of x. What that means is if you have an integral from a constant to x of some function that's of a different variable, like f of t dt. Derivatives and integrals undo each other. So when you take the derivative of an integral, you get out what you put in. But because that upper bound is the variable x, what we get out is the function f of x. That's what the first part of the fundamental theorem of calculus said. If I were to take the derivative of both sides of this equation right here, what I would have is the derivative of the natural log of x is 1 over x. Since this is the derivative of an integral from 1 to x of 1 over t dt, using this fundamental theorem of calculus, this would also be equal to 1 over x. I'm just verifying that this definition does hold mathematically using the fundamental theorem of calculus. So we could think of the natural log as an integral from 1 to x of 1 over t dt. What's going to come in handy here is remembering, first of all, what the derivative of, let's say that we have a natural log of u. The derivative of the natural log of u, where u is a function of x, a differentiable function of x, is going to be the derivative of the argument over the argument. And the integral of 1 over x dx is the natural log of x. And then we put plus c because there's no bounds on this integral. So we're going to be reviewing some concepts that we learned in Cal 1 in this section. Now, the number e, Euler's number, is a number in the domain of the natural log, satisfying the condition that the natural log of e is equal to 1. Well, we remember that from pre-cal probably. So the natural log of e is equal to 1. The derivative of natural log of u is the derivative of u with respect to x times 1 over u. Well, the way I wrote that was u prime over u. It's just an easier way for me to remember it. And the derivative of the natural log of the absolute value of x is 1 over x. Why do we have to put the x in absolute values here? What is the domain of a log function? It's all positive numbers. So if I had to graph a natural log function, the graph of that natural log function would look like this, where this becomes asymptotic to the y-axis. So we would say that the domain goes from 0 to infinity. I'm just reminding you of some properties that you've learned in pre-cal, but probably haven't looked at since pre-cal. So I'm dusting the cobwebs off of some things in your mind right now. We have this rule right here. It's the product rule for logs. It says that if you have the natural log of a product, b times x, then you could rewrite that as the natural log of b plus the natural log of x. Number 2 is the quotient rule for logs. And the quotient rule for logs says that if you have the natural log of a quotient, you could rewrite that as the natural log of the term in the numerator minus the natural log of the term in the denominator. Number 3 is just a special case of the quotient rule, because we know that the natural log of 1 is equal to 0. So this would be the natural log of 1 minus the natural log of x is negative natural log of x. We know that the natural log of 1 is 0 because the natural log function crosses the x-axis at the point 1, 0. So when you plug in a 1 in the argument of a log, you get a 0 back. And then number 4 is what we call the power rule for logs. And this says that if you have the natural log of something raised to a power, then you can bring that power in the term in the argument down front and write it as that power times the natural log of x. We'll be using these rules as we do the homework in this section. I also want to remind you of the integrals of tangent, cotangent, secant, and cosecant functions. The integral of tangent u is going to be the natural log of secant u plus c. We don't have to memorize this because all I got to do is rewrite tangent as sine over cosine and then do a U substitution and let u be equal to the cosine of x. When I integrate that, I get this. The integral of secant u is the natural log of secant u plus tangent u plus c. This one you do want to memorize. You want to commit it to memory as fast as possible because we will be using this a lot and it's worth memorizing. And then we also have the integral for cotangent u and cosecant u. Notice when I look at the cofunctions for the cotangent u, it's going to be similar to the integral of tangent u, but I switch out secant, which is 1 over cosine, for sine. And then when I look at the integral of cosecant u, we use the negative in front of the natural log, and then we switch out the secant for cosecant and the tangent for cotangent. Tangents and secants go together, cotangents and cosecants go together whenever we're looking at the rules or the properties for the integrals and derivatives in calculus. In figure 7.3, I have the graphs of y equals the natural log of x and y equals the inverse of the natural log of x, which is e to the x. Notice there's symmetry about this line y equals x. When you graph a function with its inverse, you get symmetry about the line y equals x. You learned that back in pre-cal, but like I said, you've slept since then, so just wanted to remind you of this property. We also have the inverse properties. E raised to the natural log of x is x, and the natural log of e to the x is x. So ln's and e's end up canceling each other out, and we're just left with x. If u is any differentiable function of x, then the derivative of e to the u is going to be e to the u times the derivative of u. This is from the chain rule. And then the integral of e to the u is e to the u. And then we have our properties of logs. This is a product rule, a quotient rule, negative exponents, and then a power rule. When you raise a power to a power, you multiply the exponents. If our base is a, we could rewrite a to the x as e raised to the x times the natural log of a. This is what you could do if you were going to, say, integrate something with a base a or take a derivative of something with a base of a. Use this definition to rewrite a to the x as a e raised to a power. In example 1, we are asked to evaluate the integral of 8 secant squared 4t over 7 plus 2 tangent 4t dt. This one you can only do by doing a U substitution. But what do I want to let u be equal to? Well, I'd like to let u be equal to something so that when I take the derivative of that thing, I have that derivative in my integrand, and that would then be incorporated into my du. So here I could let u be the denominator of this fraction, 7 plus 2 tangent 4t, and then when I take the derivative of a constant is 0, and the derivative of tangent is secant squared, so I've got that 2 there, and then it would be secant squared, leave the angle alone, and then by the chain rule, I have to multiply this by the derivative of the angle, and the derivative of 4t is 4 dt. I can rewrite that and simplify it to get 8 secant squared 4t dt. And then notice this is already present in my problem. That would be my du. So when I go to solve this integral, what I would do is I would rewrite this as the integral of du over u. Remember, I let the entire denominator be u, so what I have highlighted in yellow is actually what I'm plugging in for du. And the integral of du over u, we already said, is the natural log of u. But do you want to leave this as your final answer? No, the original problem had a variable of t. Your final answer has to have a variable of t. The only time you can avoid this back substitution is if you have bounds on your integral, in which case then you could change your bounds and then not go back to the original variable. So the final answer here would be the natural log of the absolute value of 7 plus 2 tangent 4t plus c. In example 2, we're given bounds for our integral, and we're asked to integrate e to the x dx. What is the integral of e to the x? It's e to the x, and then we're going to evaluate this from the natural log of 5 to the natural log of 8. Well, using the fundamental theorem of calculus, that means that we're going to plug in our upper bound minus, and then we plug in our lower bound. And then using the inverse property of e's and logs, we'd see that the e's and the natural logs cancel out here, and this is just going to be 8 minus 5, which is 3. In example 3, we have the integral of 5 e to the 5s divided by 1 plus e to the 5s ds. How would I solve this integral? What technique could I use? I want to do a U substitution, but what is U going to be equal to? It's going to be the denominator of this fraction, 1 plus e to the 5s. If u is 1 plus e to the 5s, what is du going to be? It's going to be 5 times e to the 5s ds. And we have to multiply this by 5 because the derivative of e raised to a power is e raised to that power times the derivative of that power, and the derivative of 5s is 5 when we take the derivative with respect to s. Fortunately, I have that in my numerator, so I have this entire value right here. This whole thing is going to be my du. When I rewrite this problem, then this is going to give me the integral of du over u. But what is the integral of du over u equal to? The natural log of the absolute value of u plus c. I don't want to leave that as my final answer because I don't want my answer in terms of u. I want it in terms of s. So this would be the natural log of 1 plus e raised to the 5s plus c. Did I have to use these absolute value bars? I did not have to because exponential functions e to the x is always positive, so I could have used parentheses. Would I count off if you use the absolute value bars? Probably not. Question, can I distribute this natural log across here and say, well, this is going to be the natural log of 1 plus the natural log of e to the 5s, and that's going to be 0 plus 5s. Why can I not do this? You cannot distribute a natural log across addition or subtraction, just like you cannot distribute a square root across addition or subtraction. You can only change the argument using the product rule, quotient rule, and power rule. There's no rule for separating the natural log of a sum of two numbers. So we can't do that. I just wanted to mention that. Example 4 is another definite integral. We're asked to evaluate the integral from 0 to 9 of the square root of 5 plus 1 times x raised to the square root of 5. This looks scary, doesn't it? Looks horrible. What makes it look horrible? The square roots. But look at that square root of 5. That square root of 5 is just a number, isn't it? So what if I gave you the problem 3x squared for our integrand? Would that be scary? Not as much. But the square root of 5 is just a number. Just like 2 is just a number. For this problem, you don't need any substitutions or anything. You're just going to be using the power rule to evaluate the integral. And we know the power rule. It says if you have the integral of x raised to a power, we're going to add 1 to that exponent and then divide by that new exponent. This is just x, it's a constant times x raised to a constant power. So when I integrate this, I'm going to take the constant that's out front, that's the square root of 5 plus 1. On my x, I'm going to add 1 to the exponent, so that's the square root of 5 plus 1, and then I divide by that new exponent, the square root of 5 plus 1, and then by the fundamental theorem of calculus, I'm going to evaluate this from 0 to 9. Well, when I do that, notice the square root of 5 plus 1, these factors cancel, and that's just going to give me x raised to the square root of 5 plus 1 from 0 to 9. Using the fundamental theorem of calculus, that means I'm going to plug in my upper bound. In place of x, I plug in a 9 raised to the square root of 5 plus 1 minus, and then my lower bound, 0 raised to the square root of 5 plus 1. And 0 raised to any power is 0, except for 0 to the 0, but 0 raised to a constant power is 0. And so my final answer is 9 raised to the square root of 5 plus 1. And it was not a bad problem. But what you've got to train your mind to do is not panic when you see numbers that don't look nice. Know that the square root of 5 plus 1 is just a constant. So we've got a constant times x raised to another constant power. If you can get comfortable rewriting a complicated problem as a simple problem with nice numbers, look at how you'll evaluate that nice problem and then apply those steps or that principle to the complicated problem. And then it's not so bad. The question was, why did the square root of 5 plus 1 end up at the bottom? And the answer is because of this rule right here for how we find an integral of x raised to a power. We add 1 to the exponent and then divide by that new exponent. So my power on x over here was the square root of 5. When I add 1 to it, I get the square root of 5 plus 1, and then I divide by that new power. And then those powers ended up canceling out. All right, example 5 is what we call an initial value problem, and I am fond of these types of problems. You will see one on your test like this, at least one. In this problem, we're told that dy dt is equal to 3e to the 3t sine e3 to the 3t minus 27. That's a differential equation. And then y of the natural log of 3 equals 0 is an initial condition. The instructions here would be to solve for y. And let me write it this way. When you see a problem like this, what you want to do is find the function y. So y will be a function of t, and this given condition right here, you can think of like this. This is an initial condition. That means that y is going to be equal to 0 when t is equal to the natural log of 3. This is our initial condition we'll use to take our general solution into a specific solution. So we start with the differential equation. Y prime is equal to 3e to the 3t sine e to the 3t minus 27. And if the goal is to find y and I'm given y prime, what I want to do is integrate, because integrals undo derivatives. And what we do to the one side, we've got to do to the other. So when I integrate y prime, I end up with the function y. Now, how am I going to integrate this? It's not a straightforward problem. We are going to have to use a U substitution. So what would we want to let u be equal to? It would be the angle on the sine function. Yes, it'd be e to the 3t minus 27. If that's u, what is du equal to? So here's my 3e to the 3t dt. That's where I'm going to put the du in place of. So that means that now I have y equals the integral of sine u du. And what do we get when we integrate sine? We get negative cosine. The integral of sine is negative cosine. At this point, we're going to plug in our initial value. We use the initial values to solve for c. Or once you've solved your equation, you need to use the initial value to solve for c. But I can't do that just yet. What do I got to do? What do I have to replace this u with? Got to replace it with e to the 3t minus 27, what u was equal to. So I'm going to do that replacing all at once. In place of y, I'm going to plug in 0 minus cosine of, in place of u, I'm going to plug in e to the 3t minus 27 plus c. But in place of t, what am I going to plug in? This says that y is equal to 0 when t is equal to the natural log of 3. So I replace y with 0, t with the natural log of 3, and the u got replaced with this expression that I said u was equal to. Now I need to simplify this. So let's come over here and do some scratch work. In the angle on this cosine function, we have e raised to the 3 natural log 3. I can't just cancel out this e and this ln because of that 3 right there in front of the natural log. What rule helps me move that? Remember the power rule? It says if you've got a constant times the natural log, you can bring that constant up into the exponent. So that means I could rewrite this as e raised to the natural log of 3 to the third minus 27. Now the e's and the ln's will cancel each other out, and I get 3 to the third, which is 27, minus 27, and that's equal to 0. So that means what I'm looking at here is 0 is equal to negative cosine 0 plus c. This is 0 because of this scratch work right here. Remember, the power rule for logs says that if you have the log of x raised to a power of n, you can rewrite that as n times the natural log of x. So I was given the right-hand side of this equation, 3 natural log 3, and what I did was I just moved that 3 into the exponent over here, and that's where I got 3 to the third for my argument on my log. So what is cosine of 0? So we get 0 is equal to negative 1 plus c. When I solve this for c, I get c equals 1. I'm just going to add 1 to both sides of the equation, and that means that this arbitrary constant is going to be 1. So my final answer is the function y equals, the constant is 1, minus cosine e raised to the 3 natural log t minus 27. I just put my constant in front. When I integrated this, I ended up with a negative cosine. Okay, my final answer is going to be y equals 1 plus cosine e raised to the 3t, not natural log of t. So it's 1 minus cosine e raised to the 3t minus 27. We have one more example. Example 6, and this is an initial value problem where we're given the second derivative. Well, if we're given the second derivative, the first thing we got to do is find what the first derivative is, and then from the derivative we can find what the function is. So when I say solve the initial value problem, this still means I want to find y as a function of t. Now let's talk about these initial conditions right here. This first one means that when t is equal to 1, y is equal to negative 2. And when t is equal to 1, y prime is equal to positive 2. So these are our initial conditions that we're going to use to find y. So we start with the second derivative. This d2y means take the second derivative of y with respect to t both times. So the second derivative is going to be equal to 3 minus e to the 2t. When I integrate both sides of this equation, when you integrate the second derivative, what you get is the first derivative. So this is going to be the integral of 3 minus e to the 2t dt. Now this we can integrate without any fanfare or trouble. The integral of 3 is going to be 3t when I integrate it with respect to t, minus 1/2 e to the 2t plus c. Are there any questions on how I got any part from that? If you're asked to integrate e raised to a constant times x, that ends up being 1 over k times e to the kx. We proved that, I think, the first week of class by doing a U substitution. So at this point, I'm just going to use this rule when we integrate e raised to a constant times a variable. Now we need to use this initial value to solve for c. When t is equal to 1, that means that the derivative is going to be equal to 2. So in place of y prime, I'm going to plug in 2. In place of t, I'm going to plug in 1. And then we simplify this and solve for c. So that's going to give us 2 equals 3 minus 1/2 e squared plus c. And when I solve this for c, I'm going to subtract 3 from both sides and add 1/2 e to the second. So that gives us c is equal to 1/2 e squared minus 1. Now this is what I'm going to plug in place of c right here. And that will give me my function y. So I'm going to move this up here now. So now I have y, that'll give me my function y prime. So y prime is going to be equal to 3t minus 1/2 e to the 2t plus c, but c we said was going to be 1/2 e squared minus 1. So I know y prime. How do I get y from y prime? I integrate both sides with respect to t. So when I integrate y prime, that's going to give me my function y. And when we integrate 3t, that's going to give us 3/2 t squared minus 1/2 times 1/2 e to the 2t plus 1/2 e squared minus 1 times t plus c. This constant term right here, I went ahead and treated it as one constant by putting it in parentheses. When you integrate a constant with respect to t, you're going to get that constant times t. This 1/2 right here, the negative 1/2, this negative 1/2 was already in the problem. So the negative 1/2 was already in the problem right there. But when I integrated e to the 2t, I then had to multiply by that second 1/2 because of this rule right here. So now we want to clean this up, and that's going to give us y equals 3/2 t squared minus 1/4 e to the 2t plus 1/2 e squared minus 1 times t plus c. Now I'm going to use the initial condition for the function and solve for c. So the initial condition for the function says that when t is equal to 1, y is equal to negative 2. So I replace y with negative 2, and in place of t, I'm going to plug in a 1. And so I can clean this up and say that this is going to give us negative 2 equals 3/2 minus 1/4 e squared plus 1/2 e squared minus 1 plus c. And we have some like terms that we can combine here. 3/2 minus 1, and then we have 2 e squared terms. So that gives us negative 2 equals 3/2 minus 1 is 1/2, and then 1/2 e squared minus 1/4 e squared is 1/4 e squared plus c. And when I solve this for c, that's going to give me negative 2 minus 1 is minus 5/2. Negative 2 minus 1 is negative 2.5, which is negative 5/2 minus 1/4 e squared. So this is what I'm going to plug in place of c to get my final answer. So when I replace c in this equation, I end up with y equals 3/2 t squared minus 1/4 e to the 2t plus 1/2 e squared minus 1 times t minus 1/4 e squared minus 5/2. I switched the order on these last two. There's no special reason why. And this would be our final answer. So when you have an initial value problem, you're going to be given a differential equation, and you want to find the function that satisfies that differential equation given some initial conditions. If you're given a second derivative, you have to know initial conditions not only for the function, but also for the first derivative. Any questions? Then this wraps up section 7.1.